Introduction. So the topic for our project was lung cancer. We modeled the risk of having lung cancer based on age, gender, smoking, yellow fever, and other such factors. There has been prior research done in this area before. For example, Beijing Institute of Genomics published a study where they created a model that takes patients' clinical variables as inputs and outputs the likeliness of developing lung cancer. It helped in cancer early detection, auxiliary diagnosis, prognosis prediction, and immunotherapy practice. Problem definition. Lung cancer is the most common and deadliest cancer. It is the leading cause of death worldwide. It killed approximately 1 million people in 2018. The goal of our project is to find major contributing factors for lung cancer to help decrease its prevalence in society.
For our project, we have chosen lung cancer dataset from Kaggle to predict the likelihood of individuals developing lung cancer. This dataset aggregates a variety of behavioral, environmental, genetic, and clinical factors to predict the potential risk of having lung cancer, including demographic information like gender and age, lifestyle habits such as smoking, and clinical indicators like fatigue. This will provide a comprehensive view that enables our prediction for lung cancer risk based on diverse factors.
Our current methodology can be broken down into 3 major steps. First, we plan on doing dataset preparation and pre-processing. In this step, we will visualize the data to better understand it and also clean it up to remove any discrepancies as well as make it ready for model training. Next, we will do model selection and testing. We plan on testing 3 major types of models: neural networks, logistic regressions, and SVMs for classification, as well as using unsupervised clustering to explore any patterns that may lie in the data. Lastly, we will evaluate the models and then further use those evaluation metrics to improve the performance and change the parameters. All of this we plan on doing with the scikit-learn NumPy pandas library mainly, and using matplotlib and plotly for visualizations.
Our initial focus was on ensuring the quality of our data. One of the key points we sought to reduce was the prevalence of outliers. In order to visualize this, we plotted a box plot of all the features we had. This helped to identify outliers within 2.5 standard deviations away from the mean, which we then removed from our data. For instance, outliers in the age feature were removed, resulting in a reduction from 1000 by 25 to 980 by 25 in our dataset size. Moving on to dimensionality reduction, we employed principal component analysis. This introduces the number of features as a hyperparameter in our machine learning models, as well as providing insights into the most important features of our dataset. Utilizing a variance threshold of 95%, PCA indicated that 14 principal components optimally maintained most of the explained variance, with 11 principal components sufficient to maintain above a 90% explained variance. Subsequently, we were able to discern the most influential features. Age, gender, and air pollution were the most important features in identifying lung cancer risk. We also constructed a correlation heat map, revealing intriguing patterns such as the possibility of dust allergy, occupational hazards, genetic risk, and chronic lung disease having some correlation with each other.
The clean data was passed on to the logistic regression model, where the model has to guess the level of risk from 1, which is low, 2, which is medium, and 3, which is high. The model came out with an accuracy of 97.6%, which is a very good percentage. Here is also the confusion matrix for our logistic regression. And also the table at the bottom here are the precision, recall, F1 score, support, accuracy, macro average, and weighted average. Also, the log loss value for our model is approximately 0.0923. In the context of a multi-class classification model, a log loss value is indicative of excellent model performance, suggesting that the model's predicted probabilities are very close to the actual class labels across the multiple categories. This value signifies a highly effective model in terms of predicting the correct classes with high confidence.
For our second model, we decided to train a simple neural network using the PyTorch framework on our data with a 70 to 30% test train split. The model that we used had 3 fully connected layers of 23 input neurons, and then 2 layers of 5 neurons each, and then a final output layer with 3 neurons for a risk classification for low, medium, or high risk. Over 60 epochs, we were able to predict the test data with about 97% accuracy, which we thought was pretty good. While we originally used a much larger neural network with layers of 115 neurons respectively, we realized that we can get performances at the same level with much less parameters. Additionally, when we looked at the confusion matrix for our actual predictions on the test data, we saw that the only misses really occurred when predicting medium risk data points, which we thought might be due to the fact that they can sometimes go either way if they're on the edge of low or high risk.
So for our third and last model, we chose to use a random forest. In our model, we used the scalar model. Our data was divided 50-50 training to testing. The testing data came out with 100% accuracy, which is not hard to believe since we have 500 patients in the testing and 500 in the training. So in total, we have 1,000 patients in our data. So if you had something like 100,000 patients, it would be like 99% or 98%. But 100% isn't a clear example of overfitting. It's very acceptable. As you can see in the graph, the tree cuts are very well defined. Of course, higher up in the graph, swallowing difficulty and chest pain will probably cause a high risk of lung cancer. And when you go down to the graph, it gets more specific. It includes dust and diet and snoring. And this is all very well demonstrated in the graph. Now, when we do a comparison of all three models, as you can see here in the slide, from the left we have the logistic regression, then the neural networks in the middle, then on the right we have the random forest. When we do a comparison of the graphs, you can see the logistic regression and neural networks have somewhat wobbly beginnings, then they converge to a high accuracy of, in both cases, 98.3%, but in the case of random forest, it is pretty high from the very beginning, and it converges to 100. Other than the graph and accuracies, when we compare the precision, recall, F1 score, and support, it goes in the following order in all 4 categories. First, we have the random forest, then the neural network, then the logistic regression. On average, they are in this order in each category of the 4 categories. So basically, the random forest gave us the best results.
In wrapping up our project, our primary objective was to construct robust models for predicting an individual's risk of lung cancer, a disease that stands as a significant global health concern. Ranked among the leading causes of cancer-related death, lung cancer warrants a focused exploration into risk factors for early detection and preventative measures. Through our efforts, we've uncovered crucial insights through a logistic regression, neural network, and random forest model. These models demonstrated impressive accuracy, identifying key features such as age, air pollution, and alcohol use as pivotal contributors to identifying lung cancer risk. While our current findings are promising, we acknowledge the need for further refinement and exploration. Many more factors contribute to an individual's risk profile for cancer, and larger datasets encompassing a broader array of factors and additional observations would undoubtedly enhance the depth and accuracy of our models. Understanding that the complexity of lung cancer involves multifaceted interdependencies, ongoing research and testing on more expansive datasets remain essential.